Well,
Brilliant.
thanks to my four speakers, because it was a gorgeous presentation. Just came back last night from 3,000 meters ASL from a TV documentation about the glaciers in the Eastern Alps. So I was in your area, so to speak. And this actually also brought me my affinity to mountains, brought me to deal with relief perception and how that whole thing works. And
Manfred, just a second. Your screen isn't showing full screen presentation mode at the moment. So do you want to click the present now so we can see
maybe
slides?
Now it does.
There we go. That's it.
Now it does. Anyway, what brought me to deal with 3D visualization were some studies I carried already out in the 1970s and 80s with participants, some 100 participants of alpine climbing courses, all with academic education, so educated people. And it turned out that above 60% of all these users of topographic or hiking maps were not able to derive the needed relief information spontaneously. It took quite a while, and they had to look at the rivers, they are in the valley, and so on and so forth. So more than 60%. Later on in 92, 97, and 206, I carried out a study in 16 visitor centers in the States and Iceland, including 909 participants. And that study revealed that a varying percentage between 67 and 100% of the visitors of these information centers spontaneously headed to the solid terrain models, to the landscape models, as soon as they had discovered them, even if there were most interesting high quality maps around. So this is a proof for me how attractive true 3D is. And that also led to studies at our Institute for Cartography at TU Dresden in the 90s and beginning of this century. Now, I don't want to go too much into detail. I try to balance between examples and theory, but basically we can divide the 3D effects into parallax 3D, where the parallax direction is parallel to our y-axis, full 3D, parallax in all directions of the image plane, and last not least, the before mentioned haptic relief models. Regarding the perception, we can divide into non-autostereoscopic, using viewing aids, and this is not necessarily always spontaneous, and autostereoscopic, so self-stereoscopic, no viewing aids needed, and the whole thing works totally spontaneously. And last not least, of course, we can also divide into one stereomate, two stereomates, or more than one. Since I mentioned the viewing aids, you're all familiar with the polarization glasses, the crystal eye shutter glasses, the more recent head-mounted displays, and of course, the red-green or red-blue anaglyph maps. Before coming into the actual topic of or center of my development, I want to mention these things, which many of you may have come across: parallax 3D spatial image stereoscopy, the so-called ISIs, the single image stereograms, and the single image random dot stereograms, the SIRDs. If you look into the left example, some of you, after squeezing and squinting a little bit, you might see a body-shaped heart hovering above the plane. And in the right example, in the black and white example, there is a landscape showing elongate ridges and valleys. But it takes time, and my initial idea that this would be ideal for outdoor use didn't materialize. This brought me to get into more depth about other methods. And prior to do that with you, I want to give you this short little bit of theory about the information process in 3D based on a primary model, which nowadays usually is a high quality digital terrain model. We aim at a tertiary model, a cognitive map, as we cartographers call it, which is the imaginary model of the real world in our brains. And the central user problem here again is, how long does it take to create this tertiary 3D model? And there, the display technology, which is emphasized in red here, plays a crucial role, of course. So this is one thing I wanted to tell you. And the second thing is, we frequently also call these imaginary models we create in our brain Raumbild or spatial image. Depending on the spatial perception theory, the physical display parameters, and then, of course, the famous semiology of graphics of Bertin, which eventually creates an artificial phenomenon which is spatially observed by the visual perception system. And per definition, this does not include the real physical landscape models. So let me come to the advantages and disadvantages of hard copies and soft copies. The big pluses of hard copies are 3D overviews are easily possible. You can focus onto a detailed area, and you can the big overview in no time, unfolding the map. They are usable for mass market, easy to handle, transportable, and you have a sort of natural interaction with the display. The disadvantages, they are mostly mostly a not satisfying image resolution, and they are frequently not really elastic, now more and more, and they are static in their visualization, so no dynamic phenomena can be displayed. On the contrast, the soft copy displays allow real-time calculation and thus visualization. They are flexible, that is dynamic in the visualization model, so any processes can be displayed, and this is possible by connecting with a database. The disadvantages, as we all know, are that they require hardware, means weight, power consumption, costs, and mostly they have a sort of non-natural interaction. It's different to have a display in your hand, a big display, not just a mobile phone or a paper hard copy map. Now, let's give you a few examples of hard copies. Some of you might still remember that at the ICC in Ottawa around 2000, we displayed the first holographic geo-relief map worldwide. And I dare to say this because other American and British scientists said, yeah, this is really the first one. We made an application of holographic visualization techniques using the example of the Dachstein Mountain Massif here in the Eastern Alps. And this is, I don't want to go into details. This is just to show you that holographic displays are wonderful. However, the recording using coherent light sources and this is very important, totally vibration-free setups for the recordings are pretty complex. And this is just the same. I don't go into details, but you see, you've got a beam splitter, mirrors, and so on. So this is a complicated process. However, this was already simplified. What you see here is how it really works, and I think at the first glance you can already see, hoppa, those holographic stereograms are pretty hard to produce. Means also cost. Not so cost effective. Also, the reconstruction needs white light. And this means that with natural illumination, in particular under outdoor conditions, it's pretty difficult to get a good spatial impression. Once you have an ideal illumination, it works perfect. However, once you have say fog or something, and that's when you need maps outdoors, then it's not the right tool. And as I said, it depends on light conditions and the environment, and the whole thing is pretty expensive. Now, coming back to this Dachstein massive holograms, just very much in brief. What you normally create for a holographic map is multi-stereoscopic rays, which are displayed here in the left sketch. And you actually work above the hologram plane given here in this what we call the actual map space. So this is the foundation of this pyramid, so to speak, where we display our relief, and still above the relief, hovering above the terrain, we do the lettering. And the big advantage is that you can place the lettering at a defined elevation. And once you have gorges or steep valleys, you can even define what I called a 3D placement cone of a different of a varying angle, so that you make sure that that the lettering, like here shown in the left picture, is really not touching the terrain. Like here, for instance, too long lettering doesn't work. In addition, what we did in terms of cartography for this Dachstein hologram, we made an animation. Depending on the viewing angle, you see either the letterings of the settlements, the letterings of the mountains and the total hydrography, that means the rivers, or from any direction, you always see the scale bar and the logo. Today, the most popular true 3D hard copy technique is certainly the lenticular foil display. It has a high degree of freedom, it has a stable spatial geometry, and it has multi-user possibilities. However, frequently geometric calibration is a problem. It only works for horizontal parallaxes, and it's still a comparatively expensive technology, despite the fact that it became cheaper in recent years. Now, what we basically do with this lenticular foil display is that we have our left and our right stereo mate, and we just slice them and interlace the individual stripes. And this is what you see down here. And then we place this lenticular image under a lenticular foil. The big advantage of these lenticular foil displays is that you can combine any effects like flipping, morphing, zooming, and animation with the true 3D effect. So in 3D, you can do all this. The input data used for lenticular foil displays are virtual cameras, either in a parallel or in a convergent arrangement, and you do all this by means of software. So this is just the basic principle I want to show to you. Now, what you see here is how this interlacing of the stereo mates works. Here you see one of the stereo mates, and here you see already the interlaced left and right stereo mate. And now I'm going to show you the main rays, the central rays, and depending on your viewing angle, you see what is given here above this sort of tunnel-shaped lenticular lens. Now it's not an advantage, but one fact with lenticular maps is that you only see the principal, the central rays of every lens with a normal eye base, provided you have an eye base of about 6 to 6.5 centimeters. In this central, oh, where's my, yeah, here's my pointer, in this central area here. So once you have a map of, say, 40, 50 centimeters width, you have to move, and you will only see the central part, this small part below your eyes in a well-focused way. However, basically, this is not really hampering your map reading, because you just move over the map. One example which some of you may have come across maybe around 2000, 2005 is given here. I called it a 3-in-1 example of lenticular foil cartography. It's an autostereoscopic map of Mars based on the results of the then NASA Mars mission. And you see already in this scheme here that it displays 3 different types of lenticular information sets. And by tilting the display to left or right, or moving your head, your neck, you can see the overview area given down here. You can see in even smaller scale depiction of the route of the Mars rover then, and you can go into details once you look from left and see the details of an enlargement. So this is what I call 3D or flip lenticular foil hard copy 3-in-1. It was chosen by photogrammetry, the photogrammetric engineering and remote sensing for the front cover of their journal around 2000. Finally, we produced a Pseudo 3D, a lenticular foil map of the Granatspitzgruppe, a 3,000-meter peak area in the Austrian Alps. And what we were aiming at is a 3-dimensional landscape, and above the landscape, hovering the letterings, as it's shown here in this simulation. The input data were high-resolution stereo camera DTM, a set of color aerial photography, and a classical alpine hiking map. And what the outcome was is what you see here in true 3D, a pretty nice color air photo map, however, in 3D, as I told you. And what you see here, the white parts, they're all glacier covered. This is why they are so white. And you see also here that we had a pretty comprehensive legend. So it was really a full high quality hiking map, but in 3D. So nobody had to search for to get out the 3rd dimension. The presented map was the first time mountain map ever, which could or can still be used in true 3D without artificial illumination, even once you have foggy conditions with the unaided eyes. In contrast to the frequently applied true 3D visualizations on digital displays, this hard copy map has the big advantage that it can be easily moved and viewed by several persons simultaneously. The combination of image data, artificial and natural hill shading, and as I told you, the partly hovering topographic line formation yields an optimum for the map user. Now, I spoke about parallax 3D, parallax to our eye base. You can also go in other direction using what is called integral cartography, and that is, the result is then what we call a spherical lens foil display, also called fly's eyes. This has the big advantage that you can turn the display in any direction, and you still see 3D, implying an extended viewing zone it's spatially stabler than the Parallax 3D. However, it's still in a sort of experimental status and has still a pretty poor resolution, but there is a high potential for the future. Let me now, as an add-on, show you what was presented as the 2013 ICC in Dresden. The first depiction of two superimposed geographical planes, surfaces, in one autostereoscopic map, the example of Antarctica's topography and the Southern Ocean seafloor. A paper was published in the Cartographic journal. And this is an exception from my PowerPoint because you can see it here. This is Antarctica. And what we did here is that we displayed in a net of honeycomb lines the ice surface, the shape of the ice surface, and below the actual rock surface of Antarctica. And what you see at a first glance is that in Antarctica, actually, we have not a real continent, but rather a series of individual separated islands. Anyway, regards to Ken. Ken Field selected this map for the best map selection of contemporary maps in Redlands, and I'm very glad and proud of that and thankful.
2 minutes, Manfred.
Yeah. This is only to show you that soft copy displays had a tremendous development in the last decades. I want to give you the German view of the things, just to show you. There was a company in Hamburg, however, only a single user thing. There's another company, Real, based in Dresden. They developed a different technology, however, based on eye finding, very complicated. There is another company in Jena with a wavelength selective filter array, again, high tech, very costly, and but very efficient. However, as I said, not so easily portable. Digital holography has a high degree of freedom, multi-user function, but it's still not yet fully operational, and it's again a very expensive technology. Here is one example, again from a company in Dresden, Real Technologies, but I think in recent years they only produce in Canada. Anyway, I want to give you these examples just in case anybody is interested. And last not least, you can just convert lenticular foil technology and put into the digital domain, and put a lenticular foil sheet in front of your screen. And this is what we did for the Dresden True 3D Atlas, presented at the ICC in Beijing many years ago. And here you have the LCD screen and a prism mask on top of it. And using this, you can then add interactive functions like adding fog to the landscape, or make an overflight, a fly-through over a foggy valley, and things like that.
Time to wrap up, Manfred, please.
Yeah,
Thank
we
you.
even went to, this is my last example, we even went to a film production of a historical globe, which is displayed in Dresden at the museum by Jansson Blau, using, again, a barrier mask display, and using the original data from the Austrian National Library in Vienna. We made some data processing and enhancement and so on and so forth. And using this barrier stripes display, we then generated a true 3D viewing aid free film about this ancient globe, which includes information about the publisher and the designer, Jansson Blau, the route, the trip around the world by Magellan, the round trip by Lemaire and Schouten, and finally information also in 3D about the quality and the accuracy of the image map.
That's fascinating. Thank you ever so much. I think we've just run over, so sadly we're not going to have time for questions.
I'm already going to the next presentation, and I did not purposely, initially I had it in my presentation, not mention the digital information on terrestrial landscape models like given here, but this leads already to the next presentation. Thanks a lot.